Good day and welcome to this first of a series of short videos on software communication architecture for the design and development of complex software-defined systems. I'm Claude Bellil, now retired, but formerly product manager of the Viavi Solutions software communication architecture product line. As software continues to dominate how electronic systems behave and as such is becoming a major cost element of these systems, it seems appropriate, if not essential, to reflect on how to best implement software to draw all the benefits of SDS such that in the long run, development cost and time to market can be minimized. And I'm not talking here which computer language, whether it's C, C++, or Python, or others, should be used, but rather more fundamental than that, how the software should be constructed to make sure it can easily adapt to the ever-evolving system platforms. Nothing worse, you'll admit, than writing software and finding out a few months later that it must be rewritten because some of the components have gone obsolete and the software won't run anymore. In this series, we will cover the importance of the underlying software infrastructure on which the application that defines the system will run. We will talk about how the software lifecycle, from how it gets loaded on the platform processors, connected to the different peripherals, configured with the required parameters, and then get started and stopped. We will focus on the software communication architecture, or the SCA for short. One such architecture initially developed for the military radio market, but applicable to any complex embedded systems, be it military or commercial. As the SCA is an open architecture available to all, where you can freely download the specifications, an ecosystem has emerged, and commercial off-the-shelf tools are now available to simplify the development of SCA-based systems. Using the Viavi suites, we will show the development process and the benefits of the SCA. In this series of videos, we will first define what we mean by software-defined systems, or in the case of a communication device, what is a software-defined radio? How different are they from our smartphones or our desktop computers? What are the challenges faced by the engineers when developing SDS? What did they need to facilitate and speed up their development? Then we'll look at the software architecture, or how the software is designed to meet those needs. We'll mention a number of those architectures available to standardize the development of the software with the aim of simplifying the development cost and time. In a third video, we'll focus on the software communication architecture, or the SCA. One such architecture developed for tactical military radios, but applicable to a wide variety of embedded systems, from radio, radar, electronic warfare, to robotics, instrumentations, or automotive. What is the SCA? Basically, a component-based development environment. In the fourth video, we dive a bit more into the SCA and show how it works, the internals of the SCA standards. The aim here is not to be exhaustive, but simply to demystify the SCA. In the last two videos, we will look at how applications can be easily developed using commercially available tools. So let's get started and look at what we refer to as software-defined systems in this series. So what is a software-defined system? Here's a definition that we will use. At the heart of an SDS is a computer that runs software programs to analyze, organize, modify, and input signals and make a decision to affect the output. We say it is defined by software since changing the software programs will change the behavior of the systems, its personality. As opposed to a hardware-centric system, a software-defined system can be reprogrammed to execute a different task. Much like your laptop, when you load it with word processor applications, you get a typewriter. When you load his spreadsheet applications, you get a calculator. When you load Skype, you get a telephone. Taking a radio as an example, the SDS would become an SDR, or software-defined radio. With this, the definition of an SDR, as suggested by the Wireless Innovation Forum and international organizations devoted to the development and promotion of SDS technology, states that an SDR is a radio in which some or all of the physical layer functions are software-defined. Error corrections, interleaver, modulators, demodulators, filters, synchronization, etc. On Wikipedia, you find the next definition. It's an SDR, a radio communication systems, where components that have been traditionally implemented in hardware are instead implemented by software. As the processors become more powerful, the proliferation of software-defined systems is rapidly expanding. We now find them in multiple domains as listed here. All of these domains rely on SDS technology to develop new products, as it gives them more flexibility and allows them to more rapidly introduce new features. Implementing signal processing algorithms is certainly much faster in software than it is by hardware means. In theory, this seems simple. After all, we've been doing this for decades with desktop and laptop computers, installing and running different software to emulate a typewriter, a calculator, or even a phone. But for most of the systems shown in the previous slides, the interior of the computing machine is much more complex. Those machines may have multiple processor types: general purpose processors, GPP, a graphical processing unit, digital signal processors, the DSPs, or the field programmable gate arrays, the FPGAs. They run different types of operating systems, such as Linux, VxWorks, Integrity, QNX, Lynx OS. And those are often real-time OS. They're often distributed over multiple processors and often on different computer cards. And they may come in different form factors. We are showing here examples of form factors for the radio industry, but these could be replaced with robots of different size and shape, or vehicles, or drones. As software plays a major role in the development of embedded systems, here are a few numbers worth thinking about. Over 50% of embedded systems are heterogeneous, which means they have multiple types of processors or multiple types of OS, as we've shown in the previous slides. 60% of project resources are devoted to software. And to show the importance of that software, we see that 89% of the projects attempt to reuse software from previous projects, but yet 60% of those projects finish behind schedule. When upgrading their system, the main reason given by the industry is they need new software features, or they need different processors. This number has gone up to about 50% these days to exploit the new features and performance of the latest processors. And about 25% of these projects will even migrate to new processors from completely different families of architecture or vendor. Different connectivity capability, discontinued hardware, software, different OS are some of the other reasons given by the industry to upgrade their systems. So the challenge to develop software for those heterogeneous and distributed systems are numerous. First and foremost, as we saw, the large quantity of software that must operate over multiple distributed processors running different OS is not easy. And the testing of all that software code under different conditions the radio must operate is not any easier. Then you get the system obsolescence. The speed at which the electronic is being developed and improved these days, you can hardly count on being able to find the same component over multiple generations of your product. When they were first mass-produced, manufacturers expected electronics to last roughly 40 years. By the 1990s, their lifespan was half. Today, electronics are typically used on average of 4.5 years and sometimes as low as 1.5 years. And the problem will be even bigger if the software was written specifically for the chosen hardware. Finally, inserting third-party software into the system to obtain additional capability is difficult, especially if the system is based on proprietary and closed architecture. So what are the needs? Increase the product lifecycle through constant evolution is certainly an important one. We need to reduce the development cycle to speed up the introduction of innovations. We must be able to insert technology post-manufacturing without returning to factory all the time. Another need is to support modern complex platforms like the HEADS systems with multiple OS, processors, distributed processing running on different form factors. We also need to protect the investment and minimize the cost. Since software is a major portion of the embedded system, we should be able to reuse what has been written as much as possible. This is the reuse instead of rewrite. But to be able to reuse, the software must be decoupled from the underlying hardware. We should also adopt what is available on the market and has proven itself. Again, why reinvent the wheel for every project? Move away from proprietary and difficult to maintain architectures. In the next video, we'll take a look at the software architectures, or how software is structured to meet the challenges and needs discussed above. We'll look at the open architectures, those that are available to multiple companies, as opposed to the proprietary ones that are company-specific and too often project-specific. We'll see that the software communication architecture, the SCA, is one such architecture that stands out for its applicability in multiple domains. So please join me in the next short video. Thank you very much for listening.